Hello, everyone. Thanks for coming out for this other lecture. So basically, I'm using Rstudio, the statistical package, to do a simple regression analysis that we need to understand. Now, remember regression, a bivariate analysis here. We're using continuous variables. Those are numbers, not like gender, male, female. These are continuous numbers, as you're going to see. So how am I going to get this data up? Well, with regression analysis going to quantitative research, I picked a data set, as you might know, survival. Why? Well, we're going to relate it to law and the other article you read. So basically, I take this survival thing that I have on. It has to be the CSV. I like to say CVS. But anyways, CSV, survival, right here. I'm going to import this data set into Rstudio. So this is actually quite interesting because this is going to have to do with rats, as you might know, and the radiation they have. And this is particularly important for law. So let's import this. And then here we have it. So basically we have survival rates, which is the dependent variable, and then dose, which is the amount of dose of this radiation, the independent variable. So this would be X and survival would be Y. So first we have to attach it. Remember, just because I imported this doesn't mean that it's definitely there. We have to attach it. So with Rstudio, I just attach it. What's the name of this one? Oh, survival. So I know it's on there because it should, and there it is, come up. So I attach survival. So I want to make sure it's attached. So I go dose, it's there, and then serve, which is survival, these things. Now, if you're in PETA, I apologize because these are tests, real tests on mice or rats. So if you really like mice or rats, I'm sorry, they inject them with radiation to see the extent to which they die. So again, the dose is the dependent variable and the independent variable, the cause, X, dose Y, the dependent variable, survival. Well, I got that confused. Sorry about that, mate. Basically, dose is the independent variable, X. Survival is the dependent variable, Y. I want to make sure I have that clear. Sometimes that gets fuzzy in my head. So the dose is causing or not causing the survival. So the goal here with regression analysis is that we want to see the extent to which doses of radiation, right, in mice have a survival or reduce that survival, which we are going to see. So one of the most basic fundamentals of this, the correlation coefficient, is basically seeing if there's some kind of correlation, relationship between these two things. So let's take a look. In R, we can do this by X, Y. X, again, being the independent variable dose, Y, dependent variable, survival. Okay, so we basically have what the, oh, I gotta actually relate it to them. So let's make X, since X is the dependent variable, independent variable, sorry, that is dose. So we'll make that dose. Let's take a look if it goes. All right, so there we go. And we know X represents the dose. The survival is the dependent variable, Y, which basically means serve. So now we know that's in there because of that. So basically we have Y as, let's take a look if it went through, that. So it did. So now, as some of you might know, I'm under quarantine. I could be sick. I could have the coronavirus. I miss everyone, our discussions, the people who sit up front, etc. But unfortunately, this is the way the world is going. And I do, my hat goes out to all the people whose family might be suffering because of this. There's a lot of loss of jobs, etc. I'm coughing. Do you think I could have it? I certainly hope not. So luckily, we are definitely taping this thing, and you don't have to see me. Okay, got to drink some water here. If I start coughing a lot, man, I better go somewhere. So anyways, I'm sure I don't have it. I've had many diseases. I'm fine, I swear. So anyways, I was in quarantine because I just got back from Bogota, and I went to the Florida airport. So now I'm quarantined 2 weeks in this, but I just have a tickle in my throat, I swear. So anyways, now we can do the correlation. Here we go. COR is actually for Rstudio. Rstudio, remember, is the environment, the statistical environment using R, which is also a statistical environment, but Rstudio makes this look so much nicer. So essentially here we have the correlation, and let me see if I can make this just zoom in one bit, if that's a little better for everyone to see. So now we have the correlation X, which is the independent variable, the cause, and Y, the dependent variable, what happens is that. So we get a negative 0.76. What does that mean? Well, negative, because there seems to be a negative relationship. Remember, the correlation coefficient can have a negative number. It goes up to 1. 1 is a perfect correlation. Positive means there's a positive correlation between the two. A negative number, like we see here, means that there's a negative relationship. So obviously, the more doses that a rat gets, the less survival he or she has. So it's negative 0.76. Now, is that good? Considering one would be a perfect, which we usually don't get in life, a perfect correlation, that is relationship between these two variables? Well, it depends. A lot of people say, in engineering, you need really high, and the social sciences a little less. Maybe in this case, which is the natural sciences, 0.67 is decent. It's just about, because it's 6, 7, 9, it's almost 0.7. So that's pretty strong correlation, negative correlation, which means as the independent variable dose is injected into the mice, their survival rates go down. So you get a good, remember, too, this is just R, not R squared, the Pearson R squared, when we talk about the coefficient of determination later, which we're going to see. So basically here, this is the correlation coefficient, and this is just seeing if there's a relationship, should we continue with this? So we obviously should. So what happens next? So we see that there's a correlation between these two, and it happens to be negative. Right? So what we might want to even do more so is do a deeper regression analysis. I would say it's called, so we'll call it regression, just so you remember it. And in Rstudio, the way it is, or our statistical environment, is basically LM with the dependent variable first, Y. You want to put that little guy there, I forget his name, and X. So we're calling this regression. We're giving it a name so we can get a summary of it. So basically, this is going to be regression. So now we want a summary of this regression. And here we are in all its splendor. So basically, we just did a regression analysis, and we're going to quickly go over what this means. So don't worry right now about the intercept. this is not going to be significant for us. But the estimate in the x here, which is the independent variable, is basically saying, and this is going to be very important, so I'll do it, is that with every more unit of this dose, that is of the radiation, because this is the dose of the radiation, this is the survival rate, that the rats survive 0.027 less. So what does that mean? Well, I don't really know how they measure the survival rate, but basically there's every dose that they get, you know, and you see very high doses up here, there's a less likely chance of them surviving 0.027647% or amount, whatever the data and however these scientists are measuring the survival rate. So is that good? I mean, it seems to be decent since there is a significant level which we're going to talk about. So basically, for every more unit dose of this radiation, there's this much less of a survival. And it's negative. If it was a positive correlation, obviously wouldn't have the negative thing. So that is basically very important because that's a practical number that we should be seeing with every dose. There's this much less of chances of survival for the rats. The standard error is just an estimate that if we continue to take samples of these rats, this is the area that it will be around. So we want a standard error, like the residual standard error, as we're going to talk about, to be as low as possible. And that's actually pretty low, because if you have 0.027647, you basically have a standard error of 0.008616, and that's significantly lower here. So if we kept on doing samples with the doses and survival, it might not be 0.027647. It could be 0.031 or something like that with this. It could be anywhere with this around this area. Now, this is most important. This is the student t-value that gives us our p-value. So basically, what's the p-value? We want a p-value lower than 0.05. That means that there's a less likelihood, the lower the p-value, that there's a less likelihood that this is all happening due to chance. So as you can see, we're not looking up here, we're looking here at our x variable, that it's 0.00751. That's significantly lower than 0.05, which means anything lower than 0.05 in the p-value is significant. One of the things I like about R is that it gives you these little stars. And we'll see this later with other videos where the star might be 1 star, 2 star, or 3 stars. 2 stars are pretty good, 3 is better. But it basically means, just by looking at it, the 2 stars, that it is significant. So what does this mean? This means, excuse me, that the dose of radiation is basically, excuse me, I better get checked out for this virus. The dose is due not to chance, but the survival rate and dose are correlated due to each other. That is, due to the dose, the survival rate goes down. So we can say with confidence, that is, because the p-value is under 0.05, that it is not by chance that the mice are dying, not due to random variables, but to the dose. So that's what that's saying. So for here, I really want you to understand that this is how statistics are done. Very basic statistics, but this is how they're done, right? We're looking at large N data. Here, there's 14. Notice the degree of freedom is only 12, which we're going to talk about later. But you have the independent variable dose. You have a dependent variable. variable. You have continuous variables, that is their numbers, not categorical variables. A categorical variable is like man, woman, you know, etc. Those are categories. These are continuous variables that go up and down. And what I like about this, it's not that I hate mice or I want to torture them, is that you see a dose and then you see a survival. So it's very clear. The more doses, the less survival. You see a correlation, but a negative correlation. And then we can come down here and see the estimate for every dose. There's a lack of life, negative of 0.027647. There's a standard error. That is, you know, if we keep on doing this in samples, you know, it'll revolve around kind of this number here, which isn't that bad. And then we come here and we see the p-value. If it's under 0.05, it will be significant. And this is 2 right here, and you see that it is significant. But then when we come down here and we see the multiple r squared, that is the r squared. That is Pearson's r squared. The coefficient of determination, which is basically the correlation coefficient squared, and it's 0.46. Is that good? It's not great, but it's not bad. You know, it really depends on the area you're in. As I said, I've talked to engineers and they like really high ones, like 0.8. And that's really not realistic in the social sciences or even sometimes the natural science, but it's good. It's decent. The multiples r squared is, you know, 0.46. It seems to be that there is a correlation. How much of a correlation? You know, you start seeing we're looking at different measurements. Here you have the estimate, then you have the standard error, which is low, saying that it would deviate by this much, which isn't that much, that's good. Then you have the t-value, which gives us the p-value, which shows that it's significant, which a lot of researchers depend on the p-value because it represents whether or not this is done by chance. And a p-value of over 0.05 or even 0.1 means that it might be by chance, so you don't say it's significant. So what are we doing here? Well, since we're coming to the conclusion with all these things that there's a significant relationship, negative relationship between dose and survival, we basically reject the null hypothesis, which you should know. So the null hypothesis is the idea that null, nothing, there is no relationship between these two variables, the bivariate variables, continuous variables, numbers, but there is a relationship. So we say we reject the null hypothesis, that there's no relationship between these two, and we accept an alternative hypothesis that there is a relationship between these two variables based on all this. So what I want you to understand is what regression analysis is. How is this bivariate? Right? How is this a negative relationship? You know, running the data. This is very, very important. So we have a dose, which is the independent variable, and then survival, the dependent variable. And then we start seeing that there's a wide range of different, and we're going to see later, different measurements on whether or not it's significant. This is very popular, the p-value, so we can say that our alternative, confirm our alternative hypothesis, and we reject the null hypothesis. Okay, and there's one more thing I wanted you to understand, and this is the residual standard error. This is basically kind of high. You want this as low because this is basically the residual standard error is telling us how well, generally speaking, our model is doing and helping to explain the data. And you want that as low as possible. In my opinion, this seems to be kind of high if it's 13.41, meaning that we might be off by this much of the survival rates. And if you see the survival rates, they're not that high, or the doses. So, you know, it really depends on how we're going to read this, which I'm going to go over really quick. And that residual error, standard error, you know, it seems maybe a little high to me, but then if we're dealing with the dose, the X, you know, maybe it's not that high as I was thinking because, you know, you see doses 470. So if we're off by like 13, 0.41, etc. You know, like we miss it by 13.41. If we're dealing with doses, we get, you know, a whole lot of doses, but we want, the only thing I want you to take away from the residual standard error, and it's, there are names for this. I like to think of it, like I saw in another video, and I've heard other professors say, it's just a typical error of the model, basically the extent to which how much you're off. And, you know, 13.41, it's okay, but you want it as low as possible. I would feel more comfortable if it was like maybe, you know, 6.0 or something like that. 13.41 might be a little high, because if we fail to predict the doses by this much, that's probably why you only see two stars opposed to 3, because this is significant. But when you consider these other things, you know, like particularly the residual standard error, that it doesn't explain completely why these mouse are dying. So there is a correlation, and a significant one, between dose and survival rate, a significant correlation. But the problem is, it's not like, you know, extremely significant, although people don't like to say that. They like to say it's either significant or not. But we are, you know, let's face it, we are going to be inclined, because it's significant, to reject our null hypothesis and confirm the alternative hypothesis that there is a direct relationship, although negative, with these two variables. And, you know, the residual standard error, I would like it lower, but, you know, that's what it is. And remember, the multiple R squared is showing how well our data fits, how well the goodness of fit, that to explain that this doses up here explain the decreased survival rate. So that's okay, I guess. We're still considering it significant, but I mean, it could be higher. So the standard residual standard error could be lower, and I think this multiple R squared could be a little higher, but we're still going to reject the null hypothesis because it is significant by the p-value. So radiation is an important variable, and it's also depends on what you're talking about. So like if you say, oh, this is a multiple R squared, 0.46, oh, well, that might not be good for engineering. Well, it's really good for radiation, because if you're showing any kind of relationship and decent fit, that is the R squared here, with radiation and survival, you don't want to be close to wires or whatever, however this radiation is. And this is what we're going to get into. And you want a high F statistic, which we're going to get into later, but that's basically 10.3, not that bad. And their p-value, again, here is very low. The adjusted R squared, you're not going to worry about that now. That is for when we have a multivariate regression analysis. It basically, what they find is in statistical analysis is that the more variables, independent variables, maybe you have 7, even if they're not very influential, it pushes this R squared up. So it basically penalizes you when you start putting in a number of independent variables. But for right now, just look at the multiple R squared. Now, why is this important, and how am I going to relate it to that law paper? You read a while back about a paper on law and how lawyers, since a lot of people in political science want to study law, well, this is perfect for law. How? Well, it's perfect for law, because basically you're saying, you know, if you have a case where you find all these people with radiation, you can come in and start saying, yeah, I'm representing these people, and look at these statistics. You know, it shows in mice that the more doses of radiation, there's a significant level of decrease in survival. So we can extrapolate that, what's going on with mice, to people, and that the radiation is causing health problems in these people, therefore they deserve reparation. This is how lawyers should be, although many are not trained that way. That's why I gave you the article, should lawyers be trained in statistics? They should be, because this is very helpful for a case. You know, you go up in front of the judge, the jury, etc., and say, look at what's going on with mice. You know, there's a significant negative relationship between dose, the independent variable, and survival, the dependent variable. So basically, this is good for law. Now, I appreciate everyone coming out under these very difficult times, as I got to stop coughing. I better go to the hospital after this. Under these very difficult, you're very unique and unconventional. It's a little ineffable. It's difficult to describe what's going on now. This has never happened in my lifetime, but I appreciate you people coming out, listening to this, and I would like questions in the community forum that I put up in the class. This is going to be important under regression analysis, quantitative research, continuous variables, and what kind of questions would be on a quiz? Well, what here is the independent dependent variable? Is it significant? Why is it significant? And so on. So, and how is it related to law? Why is this important to law? That's very, very important to understand. So without further ado, I want to appreciate everyone for coming out and listening to this. Quantitative research, regression analysis, and continuous variables, independent, dependent variables, etc. So thanks so much for coming out, and leave any comments in the community forum.